Hi, my name is Aaron Netherton, and today I'll be presenting my Thomas Edison State University Capstone project for Nuke 495, entitled Thorium, the Future of Energy. Philip Rowland is my partner in this project. Our objectives for this is we're going to look at what thorium is, the thorium fuel cycle, and the molten salt reactor. Some references I looked at when I was developing this was energyfromthorium.com, moltensalt.org, and worldnuclear.com. So, what is thorium? It's 90 on the periodic table, and it's what's known as a fertile material. Now, a fertile material is something that has to absorb a thermal neutron in order to become a fission material. And this fission material is what will fission if it absorbs a thermal neutron. Some fission materials are uranium-235 and plutonium-239. It's 3 to 4 times more abundant than uranium. It's common in the Earth's crust. And it has a 14.05 billion year half-life, which is why it's so common. Now we're going to look at the thorium fuel cycle. First, you start off with one of these fission materials, most likely uranium-235, fissioning, and it will produce neutrons that will be absorbed by our thorium-232. So thorium-232 is the only natural isotope of thorium found in nature. This thorium-232 absorbs a neutron, becomes thorium-233. Now the thorium-233 will quickly decay into protactinium-233. And this protactinium-233 will then decay over a month into uranium-233. Now we're in business. This uranium-233 is another one of these fissile materials, but it does not exist in nature. Now that we have our uranium-233, we can continue this chain reaction without any other elements, any other catalysts. So now we're going to talk about molten salt reactors. The original molten salt reactor was developed by the U.S. Air Force to build a nuclear-powered bomber. Now the intention was to use this bomber in case if the U.S. ever went to war with the USSR and we needed to fly over Russia to start World War III. Since then it became unnecessary, so eventually the Air Force dropped it. But research continued for 20 or so years. The people actually working on the original project thought it was a bad plan to have a nuclear power plant on a airplane, but they were excited about it because then they could develop something that would be productive for humanity in the future. The plant that we're going to look at is called the Liquid Fluoride Thorium Reactor, or LIFTR. This is a theoretical plant that could be in development in the next few years. These plants operate at 850 to 950 degrees Fahrenheit at atmospheric pressure. So what is the worst thing that can happen at a nuclear power plant? A loss of pressure. You can't have a loss of pressure. It's impossible. You can't have boiling in the core because you're already at atmospheric pressure. So a meltdown really can't occur. And the fuel salts are made out of lithium fluoride, beryllium fluoride, and your uranium-233 fluoride. Alright, so this is a simplified diagram of LIFTR. In the middle, as you can see, we have a reactor. This reactor has two molten salt loops flowing through it. You have your fuel salt, and then you have your thorium blanket salt. So this fuel salt cycles through, goes through a salt-to-salt heat exchanger, and then comes back into the reactor. At this salt-to-salt heat exchanger, heat is passed from the second molten salt onto a gas, And then this gas is used to turn a gas turbine, which is where we get our electricity from. Now, in the reactor core, that's where most of our fissioning is occurred. So we have lots of fission, we have lots of neutrons flying around. The thorium blanket outside of this fuel salt is absorbing any of these neutrons that come to it. And then when it absorbs the neutrons, what does it do? It gets changed into uranium-233. So this thorium blanket is also flowing continuously through here. It goes through this fluorine volatility chamber. Now in here, it gets hit with fluorine gas. This fluorine gas takes the uranium fluoride, turns it into UF6, which is a gas, causes it to bubble up to the top, and then it gets moved over to your uranium reducer chamber. Now this uranium reducer chamber bombards it with hydrogen. So this hydrogen then strips off that fluorine gas that we just took. So it turns it into UF4, which is your uranium fluoride, which happens to be the exact fuel that we're using. So this fuel that was in the blanket is now flowing into the core. Pretty cool, huh? The thorium doesn't get touched by the fluorine gas. It just continues to go through and get cycled through the fluorine blanket. Now this hydrogen fluoride also goes through this electrolyzer. In an electrolyzer, you run a current through something and it separates it into two different gases, depending on its charge. So this is the basic premise of how the molten salt reactor works. So in conclusion, thorium is an abundant and untapped source of nuclear fuel that, if used properly, has the potential to power the world for years to come. Thank you.